Okay guys, now we are going to go for the new chapter on the steam power cycle. And before that, just to recap back what we have learned in thermodynamics about the Carnot cycle in the second law of thermodynamics chapter. The second law of thermodynamics chapter, the Carnot cycle, is referred as the best heat engine or the theoretical limit of a heat engine. And if we look on the gas cycle type of Carnot cycle in the thermodynamics, we can see that the first process or the Carnot cycle comprises of four processes. One is called as the 1 to 2, is called the reversible isothermal expansion, and then 2 to 3 is called as the reversible adiabatic expansion, and then 3 to 4 is called as the reversible isothermal compression, and then the last one is 4 to 1 is called as the reversible adiabatic compression. And this can be presented by a closed system, a piston cylinder cycle, as shown right here. And based on this temperature scale, we can have that the ratio of heat at QH, which is the heat supplied, compared to the ratio to the Q rejected at QL for a reversible case, it can be substituted as TH divided by TL. And in this case, the TH is equal to T1 and equal to T2, while the TL is equivalent to T4 and also for the T3. So we can rewrite the thermal efficiency or the theoretical limit of our second law of thermodynamics for heat engine. This is for any heat engine, whether it's reversible, impossible, or irreversible. It can represent as the thermal efficiency is equal to 1 minus QL over QH. And based on this ratio of temperature scale, we can rewrite that for a Carnot cycle, we can write that as 1 minus TL over TH. So this is what we have learned in thermodynamics. Okay, but right now, what we are going to do is to look on the Carnot cycle is we apply the water as our working fluid. In this case, it's called as steam. Steam originate from water, H2O. And for a Carnot cycle, for steam, we have four main components, which is the boiler, the turbine, the condenser, and the compressor. And for the boiler, we can see that the process is the same as from 1 to 2 in our gas cycle for Carnot. It is the isothermal reversible expansion from 4 to 1. Right? This is 1 to 2. I substitute this as 4 to 1. And then from 1 to 2 is the reversible adiabatic expansion, known also isentropic expansion in turbine. And then from 2 to 3 in the condenser, which is known as the isothermal reversible compression. And lastly is 3 to 4 represent the isentropic compression, or also known as the reversible adiabatic compression. So as far as this heat and work is concerned, we can write this as the work output from the turbine. This represented by W12, and then this will be representing the heat input, the heat rejected in the condenser, and this can be put as the Q23 rejected, Q223, and then this is the work input to the compressor, can be represented by W34, and lastly is the heat supply to the boiler, which can be represented as Q41. So this is all this energy transfer by heat and work. Okay, for the turbine, of course, we are going to have the work output out from the turbine. And for a Carnot cycle that represent for steam as the working fluid, we can have the 4 processes only if we operate the cycle underneath the dome, which is as saturated condition, whereby this W12, this will represent the expansion process W12, and then the heat rejected W23, this is our rejected heat 23, which is also known as the isothermal reversible compression. And then for the compressor, we can find that this is our W34, and lastly is the heat input to the boiler, to the water, which is represented by Q41. So this is how we sketch the processes or the Carnot cycle based on steam as our working fluid. And from this expansion process 1 to 2, we can find that this is also as S1 is equal to S2, and this is equivalent to a value of Sg at T1. And then after that, we can look at the compression process. At the compression process, we can also write the entropy, which is S3, which is equal to S4, and this S3 equal to S4 represented by a value of SF at the temperature of T1. Okay, at the temperature of T1. And remember that the value of T in this case, this is as from 4 to 1 is saturated liquid up to saturated vapor. Therefore, the T1 is, we can write T1 is equal to T4. Whereas for the case of T2, we can write the T2 is equal to T3. Okay, and also the value of T4, which is equal to T1, we can find that the T1 is equal to T4, which is equal to the saturation temperature at the pressure of P1 or the high pressure side. Whereas the T2, which is equal to T3, and this is also equal to the T saturation or the T sat at the given pressure at low side, which is the condenser pressure. Okay, so this is how we can write this value, or look at the value of heat transfer, the values of heat transfer or the energy transfer in terms of Q41, W41, R23 and 34. So what's next we are going to do is to look in depth on the Carnot steam cycle, and we are going to look upon the thermal efficiency of this Carnot steam cycle. How do we solve that? By looking at the entropy principle or the change of entropy principle, and also based on the steady flow energy equation applied to a flow device. In this case, our flow device comprises of 4 main components, which is the boiler, the turbine, the condenser, and also for the compressor. Right? As far as for the Carnot cycle is concerned in thermodynamics, on the second law of thermodynamics, we can find this is our final equation. Okay, final equation. So we are going to prove that when we learn in thermodynamics, this equation can be represented also for a Carnot cycle, and we are going to prove that it will be the same format of this type of presentation of the Carnot heat engine. Okay, So now we are going to look on the thermal efficiency of a Carnot cycle using steam as our working fluid.